Welcome all students in the course of Data Communication Networking, BE 7th semester Electronics and Communication Engineering. We are discussing the unit physical layer, and topic is data and signals. We have seen in our previous session that bit rate, bit length, digital signal is a composite, analog signal, application layer, attenuation, distortion and noise. In this session, we are continuing with the basic concept of data and signals further. So let's start today's session. So, the data rate limits. A very important consideration in the data communication is how fast we can send the data in bits per second over a channel. Data rate depends on the three factors. First is the bandwidth available, second is the level of signal we use, and third is the quality of channel or the level of noise. So these three are the important factors which are related to the data rate limits. In this session, we are going to see following topics: noiseless channel in the Nyquist bitrate, noisy channel, Shannon capacity, and using both limits. The two theoretical formulas were developed to calculate the data rate, one by Nyquist for a noiseless channel and another by the Shannon for the noisy channel, as we have seen this brief review. So first is noiseless channel, or we can say that it is a Nyquist bit rate. For the noiseless channel, the Nyquist bit rate formula defines the theoretical maximum bit rate as equal to 2 into bandwidth into log base 2 L. In this formula, the bandwidth of the channel, and the L is the number of signal levels used to represent the data, and the bit rate is the bit rate at its bits per second. According to the formula, we make think that given a specific bandwidth, we can have any bit rate we want by increasing the number of signal levels over here. Fine. Although the idea is theoretically correct, practically there is a limit. When we increase the number of signal levels, we impose a burden on the receiver also. If number of levels in the signal is just 2, the receiver can easily distinguish between 0 or 1. Fine. If the level of signal is 64, then the receiver must be sophisticated to distinguish between the 64 different levels. In other words, increasing the number of levels of the signal reduces the reliability of the system. Fine. So there will be some consideration in our level consideration. So we can say that the increasing the level of the signal may reduce the reliability of the system, as we have seen in our equation. Let's have an example. Does the Nyquist theorem bitrate agree with the intuitive bitrate described in the baseband transmission? Solution: they match when we have only two levels. We said in the baseband transmission, the bitrate is 2 times of the bandwidth if we use only first harmonic of the worst case. However, the Nyquist formula is more general than what we derived intuitively. It can be applied to the baseband transmission and modulation. Also, it can be applied when we have 2 or more levels of signals. So consider a noiseless channel with a bandwidth of 3000 Hz transmitting a signal with 2 signal levels. The maximum bitrate can be calculated as we have known. The bitrate equation is equal to bitrate is equal to 2 into bandwidth into log base 2 into L. So put the above value, we find that it is equal to 6000 bps. Another example, having same noiseless channel transmitting the signal with 4 levels, the maximum bitrate can have 12,000 bps. Another example. We need to send 265 kbps over the noiseless channel with a bandwidth of 20 kilohertz. How many signals level we do need? We just rearrange the formula and find out our level with the help of the log table, or we can find that with the help of the calculator, that the number of levels required to transmit the data is 98.7 levels. Since this result is not the power of 2, we need to either increase the number of levels or reduce the bit rate. If we have 128 levels, then the bit rate should be 280 kbps. If we have 64 levels, then bit rate is a 240 kbps. Next is noisy channel. In the previous discussion, the noiseless channel is required. Means there is no external noise available in our channel. Over here, the real scenario, a real environment scenario is there. So thus, noise is added in our channel. So we have to consider the noise as a one parameter of consideration. In reality, we cannot have a noiseless channel. The channel is always noisy. In 1944, a Shannon introduced a formula called a Shannon capacity to determine the theoretical highest data rate for the noisy channel. So the equation is the capacity of the channel is equal to bandwidth into log base 2 into 1 plus SNR. In the formula, the bandwidth is the bandwidth of the channel, SNR is the signal to noise ratio, and the capacity is the capacity of the channel bits per second. Note that in the Shannon's formula, there is no indication of the signal level. Fine? There is no L are there, which means that no matter how many levels we have, we cannot achieve a data rate higher than the capacity of the channel. In other words, the formula defines the characteristics of the channel, not the method of transmission. Means it will show the characteristics of the channel. Let's have an example. Consider an extremely noisy channel in which the value of the signal to noise ratio is almost 0. In other words, the noise is so strong that the signal is in the fade. For this channel, capacity C is calculated as C is equal to B log base 2 1 plus SNR. We put the C is equal to 0. This means that the capacity of this channel is 0 regardless the bandwidth. In other words, we cannot receive any data through this channel. We can calculate the theoretical highest bit rate of a regular telephone line. A telephone line normally has a bandwidth of 3000 Hertz, or we can say that 300 to 3300 Hertz assigned for the data communication. A signal to noise ratio is usually 3162. For this channel, capacity is calculated as our equation that C is equal to B log base 2 1 plus SNR. We put this value, we find that we got the channel capacity is 34860 bps. This means that the highest bit rate of the telephone line is 34860 kbps. If we want to send the data faster than this, we can either increase the bandwidth of the line or improve the signal to noise ratio. The signal to noise ratio is often given in decimals. Assume that then SNR in dB is equal to 36 and the general bandwidth is 2 MHz. The theoretical channel capacity can be calculated as SNR in dB 10 base 10 SNR. So we can find the value as 3980. Then we can say that C is equal to B log 2 1 plus SNR is equal to 24 Mbps. So we can get channel capacity is equal to 24 Mbps. For a practical purpose, when an SNR is very high, we assume that SNR plus 1 is almost the same the SNR. In this case, the theoretical channel capacity can be simplified as C is equal to B into SNR dB by 3. For example, we can calculate the theoretical capacity of the previous example as we have seen over here, 2 MHz into 36 by 3 is equal to 24 Mbps. Suppose we use both the limits, then in practice we need to use both the methods to find out the limits and the signal levels. Let's have an example to prove this. We have a channel with a 1 MHz bandwidth. The SNR for this channel is 63. What are the appropriate bit rate of the signal level? So we solve this. First we use the channel formula for the find the upper limit. C is equal to B log base 2, 1 plus SNR, we find 6 Mbps. The channel formula gives the 6 Mbps, the upper limit. For the better performance, we choose the something lower, 4 Mbps for example. Then we use the Nyquist formula to find out the number of signal levels. So we can take 4 Mbps as the signal's capacity is equal to 2 into 1 MHz log base 2 L is equal to 4. So we can say that the channel capacity gives us the upper limit while the Nyquist formula tells us how many levels we need. Fine, by showing this example. Performance. Up to now, we have discussed the tools of transmitting data, signal levels, or over the network and how the data behave. One important issue in the networking is the performance of the network. How good it is. We discussed the quality of service and overall measurement of the network performance later in the later chapter 24. In this session, we introduce the terms that we need to for a future chapters, just like bandwidth, throughput, latency or delay, and bandwidth delay product. Bandwidth. One characteristic that measures the network performance is the bandwidth. However, the term can be used in the two different contexts with the two different measuring values: bandwidth in hertz and bandwidth in bits per second. So bandwidth in hertz. We have discussed this concept. Bandwidth in hertz is the range of frequencies contained in a composite signal or the range of frequency as a channel can pass. For example, we can say that the bandwidth of the subscriber telephone line is 4 kHz. Bandwidth in a bit per second. The term bandwidth can also refer to as the number of bits per second that a channel, a link, or a network can transmit. For example, one can say that the bandwidth of the fast Ethernet network or the links in the network is a maximum of 100 Mbps. This means that this network can send 100 Mbps. So what is the relation between these two? There is an explicit relationship between the bandwidth in hertz and bandwidth in bits per second. Basically, we increase the bandwidth in hertz means the increase in bandwidth in bits per second. The relationship between them depends on the whether we have baseband transmission or the transmission with modulation. So we can say that in the networking, we use the term bandwidth in the two contexts. The first, the bandwidth in hertz refers to the range of frequencies in the composite signal or the range of frequency that channel can pass. Second, the bandwidth in bits per second refers to the speed of the bit transmission in the channel or link. Fine. An example shows the bandwidth of the subscriber line is 4 kHz of a voice data. The bandwidth of this line for the data transmission can be up to 56,000 bps using the sophisticated modem to change the digital signal to the analog. Another example shows if the telephone company improves the quality of the line and they increase the bandwidth to 8 kHz, we can send 112,000 bps by using the same technology as mentioned in our previous example. Throughput, one of the important parameters to be considered for our channel. The throughput is the measure of how fast we can actually send the data through the network. Although, at a first glance, the bandwidth in a bits per second or the throughput seems the same, but they are different. A link may have a bandwidth of BPS in B, but we can only send T BPS through this link with T is always less than B. Means T means throughput, B means bit rate or bandwidth. In other words, the bandwidth is proportional to the measurement of the link. The throughput is the actual measurement of how fast we can send the data. For example, we may have a link with a bandwidth of 1 Mbps, but a device is connected to the end of this link may handle only 200 kbps. This means that we cannot send more than 200 kbps through this link. Imagine a highway designated to transmit 1000 cars per minute over a one point to another. However, if the congestion on the road, this figure may be reduced to 100 cars per minute. The bandwidth is 1000 cars per minute, where the throughput is 100 cars per minute. Fine. So you can better understand with this example. A network with bandwidth of 10 Mbps can pass only average of 12,000 frames per minute, with each frame carrying an average of 10,000 bits. What is the throughput of this device or network? We can calculate the throughput as throughput is equal to 12,000 into 10,000 upon 60 is equal to 2 Mbps. The throughput is almost the 1/5 of the bandwidth in this case. Next is latency or delay. The latency or delay defines how long it takes for our entire message to completely arrive at the destination from the time the first bit is sent out from the one source. We can say that the latency is made for 4 components: propagation time, transmission time, queuing time, and processing delay. So our equation will become like this: latency is equal to propagation time plus transmission time plus queuing time plus propagation delay. So do you think that what is a propagation time? The propagation time means it measures the time required for a bit to travel from the source to the destination. The propagation time is calculated by dividing the distance by the propagating speed, as shown in this equation. The propagation speed in electromagnetic signal depends on the medium and on the frequency of the signal. For example, in vacuum, the light is propagated with the speed of 3 into 10 raised to 8 meter per second, and it is lower in air and it is much slower in a cable. An example: what is the propagation time if the distance between the 2 points is 12,000 km? Assume the propagation speed to be 2.4 into 10 raised to 8 meter per second in cable. We can calculate the propagation time as the given equation. We got 50 milliseconds. The example shows that a bit can also go over the Atlantic Ocean in only 50 milliseconds if there is a direct cable between the source and the destination. Transmission time. We have used transmission time over here. So what is the transmission time? In data communication, we don't send just a one bit, we send a message. The first bit may take a time equal to the propagation time to each of these destination, and the last bit also take a time about time of it. However, there is a time between the first bit leaving the sender and the last bit arriving the receiver. The first bit leaves the earlier and arrives earlier. The last bit leaves the later and arrives later. The time required to transmission of a message depend on the size of the message and the bandwidth of the channel. So we can say that the transmission time is equal to message size upon bandwidth. What are the propagation time and the transmission time for the 2.5 kilobytes message and email if a bandwidth of a network is 1 Gbps. Assume that the distance between the sender and the receiver is 12,000 km and the light travels at a 2.4 into 10 raised to 8 meter per second. We can calculate the propagation and the transmission time as shown in the next slide. Propagation time is equal to 12,000 into 1000 upon 1.4 into 10 raised to 8. We can get 5 millisecond, and transmission time 2500 into 8 upon 10 raised to 9 is equal to 0.020 millisecond. Note that in this case, because the message is short and the bandwidth is high, the dominant factor is the propagation time, not the transmission time. The transmission time can be ignored. Okay. One example also shows for the image. Our previous example is for email, and this example is for an image. Now, what are the propagation time and the transmission time for a 5 megabyte message, particular image, if the bandwidth of the network is 1 Mbps? Assume that the distance between the sender and the receiver is 12,000 km and the light travels at a 2.4 into 10 raised to 8 meter per second. We calculate the propagation time and the transmission line as we seen over here. The propagation time is 12,000 into 1000 upon 2.8. Then we get 15 millisecond. The transmission time we get 40 seconds. Note that in this case, because the message is very long and the bandwidth is not very high, so the dominant factor is the transmission time, not the propagation time. So the propagation time can be ignored. Next is queuing time. The time needed for the each intermediate or end device to hold the message before it processed. The third component in the latency is queuing time. We can define the time is needed for the each intermediate or end device to hold the message before it can be progressed. The queuing time is not a fixed factor. It changes with the load imposed on the network. When there is a heavy traffic on the network, the queuing time increases. An intermediate device such as a router queues the arrived message and processes them one by one. If there are many messages, each message will have to wait. So in the last case, the bandwidth delay product. In the bandwidth and the delay are the two performance metrics of a link. However, as we will see in this later in the chapter, what is very important in the data communication is the product of the two, the bandwidth delay product. Let us elaborate this issue using some case studies. The case number 1. As you can see in this figure, let us assume that we have a link with bandwidth of 1 Bps, unrealistic, but good for our demonstration purpose. We also assume that the delay of the link is 5 seconds, also unrealistic. We want to see what is the bandwidth delay product means in this case. Looking at the figure, we can say that this product 1 into 5 is the maximum number of bits that can fill in the link. There can be no more than 5 bits at any time on the link. Case number 2. Now, assume we have a bandwidth of 4 Bps. A figure shows that there can be maximum 4 into 5 is equal to 20 bits on the line. The reason is that each second there are 4 bits on the line and the duration is 0.25 seconds. The above two cases shows that the product of the bandwidth and the delay is the number of the bits that can fill the link. This measurement is important if we need to send the data in the burst and wait for the acknowledgement on the each burst before sending to the next one. To use the maximum capacity of the link, we need to make the size of our burst 2 times the product of the bandwidth and delay. We need to fill up the full duplex channel 2 direction. The sender should be sent a burst of the data is equal to 2 into bandwidth into delay bits. The sender then waits for the receiver acknowledgement for the part of the burst before sending to another burst. The amount 2 into bandwidth into delay is the number of bits that can be transmission at any time. So we can say that the bandwidth delay product defines the number of bits that can fill the link. An example, we can think that about the link between the 2 points is a pipe. The cross section of the pipe represents the bandwidth and the length of the pipe represents the delay. We can say that the volume of the pipe defines the bandwidth delay product as we can see in this figure. So it is a cross section is a bandwidth and the length is delay, and our volume shows the bandwidth into delay. The last point, jitter. The another performance issue that is related to the delay is jitter. We can roughly say that the jitter is a problem if the different packets of the data encounter different delays and the application using the data at the receiving side is time sensitive, just like audio, video, for example. If the delay for the first packet is 12 milliseconds, for the second is 45 milliseconds, and for the third is 40 milliseconds, then the real-time application that uses the packet endures the jitter. We will discuss jitter in the later chapter in detail. So up to now, we just concluded the topic data and signals in this session. We have seen in this session is the noiseless channel, like a Nyquist bitrate, noisy channel, have a Shannon capacity, bandwidth, throughput, latency, and lastly bandwidth delay product. So we have completed the data and signals entirely from this session. Write down following question in your notebook. Ask any query in our comment section. Thank you, student. See you in the next session.